Hello everyone, I'm Alvandi. Good time, hope you're great and full of energy. It's my pleasure to present this scientific result to you as one of the member of our research team. I'm also proud to serve you that we made this scientific achievement together with two of my scientific co-workers named Mr. Mohammad Shahraeini and Ms. Shahla Khormali from the Department of Electrical Engineering from Gulistan University. However, today I want to explain the results and general description of our research, which entitled as Optimal PMU Placement Considering Reliability of Measurement System in Smart Grids in form of a presentation of your service. I'd like to begin with a list of the heading of each title. Generally, you see 14 sections. First of all, we will deal with general explanations and basic theories. Then we will explain the computational parts of the research. In addition, not only will you be familiar with the methods used in this article, but also with the simulations used in this article. Finally, at the end, I will present the results. So let's get started. First, I'm going to tell you about a phase measurement unit. The phase measuring unit is a new device that was recently introduced to the power system. This equipment is capable of measuring the phase and frequency of voltage and current waveforms and sending this data in a wide geographical area by using GPS and digital signal processor and benefiting from modern telecommunication networks. A state estimation is the calculation of the exact state of the system using imprecise and erroneous measurements. The mode in power system is the bus voltage size and the bus voltage phase, except bus number 1. For an n-bus system, the mode vector x has dimension n equal 2n minus 1. In the case that the number of measured parameters in the network is n, the state estimation equations are in the form of case 1, as you see below, where Z is the measurement matrix, E is the measurement errors, and both have dimensions n multiple 1, and Hx is the network equations that relate the measurement to the states of the network and has dimension m multiple n. A state estimation is in two forms, linear and non-linear. In state estimation, in order of the H matrix is very important and determines the observability of the systems. If rank H is equal to n, the system is fully defined. If rank H is greater than n, the system is overdefined, and if rank H is smaller than n, the system is underdefined. The observability of the power system means the calculation of network variables in order to estimate the state of the system. If the data needed to estimate the state is not available, the network will not be observable. Suppose that the entire electric network is represented by a continuous and undirected graph GVOE, so that we are the vertices of the electrical network buses and E are the edge in this graph of transmission lines. This graph can be expressed using adjacency matrix. According to the definition for a graph with n vertices, the adjacency matrix A is an n multiple n matrix whose domains are defined as follows, as you can see in formula 2. From the adjacency matrix, a generalized adjacency matrix can be formed, which is defined as follows, as you can see it as formula 3 in this slide. In this formula that you can see, I see I is the same matrix with size n, and J is this square matrix of dimension n, all of which are equal to 1. The special case x equals z equal 1 and y equals 0 creates a generalized adjacency matrix A plus, which is used in analyzing the topological observability of the graph using PMU, which we will talk about in relation to topological observability in the next slide. There is another method to calculate the observability of the system, which we call topological observability. Topological observability determines the observability of the system by using the basic of graph theory as well as the type and location of observable measurement devices. A system is topologically observable if the following condition holds. As you can see in formula 4, in this formula A plus is the generalized adjacency matrix, the PMU vector is the n-dimensional vector that specifies the location of the PMU, and the I-dimensional vector is the n-dimensional vector whose all domains are 1. In this regard, the word larger means that each lake is larger. The problem of optimal PMU placement, which is known as optimal PMU placement, aims to fulfill an efficiency goal by placing the minimum number of phase measurement units or to achieve maximum efficiency with minimum cost. In general, there are two different types of OPP. The first type is OPP with economic goals, and the second type is OPP with efficiency goals. And the goal of efficiency in both types of OPP is the observability of the entire system. In this research, we consider OPP of the first type, that is OPP with economic goals, and the desired efficiency is defined by the observability of this entire system. According to the issues raised up to now, the problem of placement of phase measurement units is in the form of an optimization problem and can be expressed in the form of Formula 5 that you can see. What can be deducted from equation 5 is that this equation problem tries to place PMUs in the buses of the power system that have the largest number of bus connections or transmission lines connected to a bus, and the type and the quality connections are not important. So the number of the bus connections is important and focuses on it, and the type and quality of these connections are not important. Before this, it was shown how to structurally check the observability of the power system using the generalized adjacency matrix. Also, using this analyzing method, the optimal placement of phase measurement units was introduced, and the investigation of these issues shows that the above method does not make any distinction between different transmission lines and only tries by placing PMUs in buses with top connections with a minimum number of PMUs to make the network visible. The main advantage introduced in this method is actually not weighted or weighting the transmission lines. Now we introduce a method that tries to place PMUs on branches with lower failure rates by weighting transmission lines. Reliability is used to weight transmission lines. Reliability, in fact, is the probability of success in performing a task, or the probability that the system or set will perform the assigned task without failure, with the limits set in the design or the time or place limits, and in a specific operating conditions such as temperature, humidity, vibration, etc. The reliability of the transmission line E, according to its characteristics, i.e. length and power, is defined as Formula 6, where lambda E is the failure rate of the line E in a period of time T. T is usually chosen as 1 year, and CBE is the electrical gap of edge E, which we'll examine together in the next slide. Electrical betweenness. Okay. The electrical betweenness of an edge is defined as the ratio of the total power transferred between the production buses and the load buses through that edge to the total power consumed in the network, whose relationship is in the form of Formula 7, where N is the total number in the power network buses, sigma ST is the number of shortest path from the production bus S to the load bus T, rho ST is the total power of the mentioned path that passed through branch E, and rho sigma load is the total power. It is the system load, and that you can see. Having the reliability of the lines, we can define a new adjacency matrix. We can generalize the adjacency matrix as weighted adjacency matrix. That our goal is to optimize the location of PMUs in the power network, and you can see in case 8 that in this matrix I omega is a square matrix of order n, which represent the importance of buses, and the reliability of lines in network is power. N is a number of buses. If we assume that we have ICCKE or n multiple n, ICCKE is the importance of bus K, and IKL provide that K is opposite to L, and K is equal to 1 to n. Therefore, the reliability of the connected line is between the K bus and the L bus. If AKL is equal to 0, it means that K bus is not connected to L bus. In this research that we conducted, the weighted adjacency matrix AKK equal to 1 means near zero failure in PMU buses, and AKL, which indicates the reliability of the transmission lines, can be calculated from the equation 6 that we stated earlier. By obtaining the weighted adjacency matrix, the observability of the system is checked using the equation 9 that you see. If we multiply the weighted adjacency matrix I omega by the vector that shows the location of the PMUs, and the resulting vector has all its domains greater than 0, the system is observable. I omega is the weighted adjacency matrix with dimensions n by n. The PMU vector is the n-dimensional vector that specifies the location of the PMUs in which buses they are located, and the 0 vector is the n-dimensional vector whose all buses are 0. Now, we will calculate the reliability of the measurement system. The relationship I omega in the PMU vector is greater than the 0 vector that we saw before. It determines whether the power system is observable with the PMU vector measurement set or not, which is theoretically no different from the relationship 4 that we saw before. And information about the reliability of the measurement system is not provided. Reliability information lies in I omega and must be quantified. It is assumed that the reliability of PMU voltage channels is 100%. It's also assumed that the occurrence of errors in two separate PMUs are independent of each other. As a result, larger levels equal to 1 in the product of the first formula means the condition that the measurement of the bus mode corresponding to that level is guaranteed. And in other words, let's say that its reliability is 100%. According to these explanations, the XR vector is defined as the following form as item 10, where XRI is the ith line of the XR vector. Deviation of the vector XR from the ideal state or the same vector, that is 1, is a quantitative expression of the reliability of the measurement system. The reliability of the SR mode is defined by formula 11, that the lower the SR is the better reliability of the measurement system. In this slide, you can see the formula that can be written and shown in the following form of the form to the solve problem of PMU with the approach of increasing the reliability of the measurement system. Now let's move to our simulation and results. To prove the effectiveness of the method presented in the design of the measurement system with high reliability, two IEEE network, i.e. 14 and 24 bus networks whose reliability information is available, were selected, and PMU placement was carried out with the two approaches of relation 5 and 12, which we said earlier is done. The reliability information of the 14 bus network is listed in table 1 that you can see. As you can see, the highest reliability is 0.98 and the lowest reliability is 0.67, as you can see in the table. Now you can see table 2. As you can see, the optimization that we discussed in 5 above only aims to ensure the visibility of the entire network with the minimum number of PMUs. As we have seen, in addition to minimizing the number of PMUs, formula 12 minimizes the value of SR, which makes the reliability of the design estimator higher. This can be proven with a PMU implemented by optimizing item 12 and the information in table 1 that we saw in the previous slide, because the links with lower reliability, such as branch 12 between buses 13 and 14, are represented in the plan. They have no role with item 12. Also, with the same number of PMUs, the approach introduced in this research has the ability to design an estimator with higher reliability. This figure represents histograms of the transmission lines which are involved in two different measurement systems obtained by optimization described in formula 8 and 17 for the IEEE 14 bus network. As can be clearly seen, the reliability of the CT measurement in the proposed method has better conditions, and this indicates the capability of the proposed method in designing a more reliable state estimator with the same number of PMUs. In this research, a method has been proposed that provides two goals at the same time. In the PMU placement, the number of PMUs is minimal and the reliability of the measurement system is high. Reliability enhancement is provided in such a way that the links that the PMU measures their flow have more reliability, and as a result, the measurement system is more reliable. By using the weighted adjacency matrix and defining a parameter called SR, this issue has been achieved. The simulation results for two networks of 14 and 24 both show that the proposed method with a minimum number of PMUs can provide a more reliable measurement system. Okay, it brings me to the end of my presentation. If you have any question, I can answer you. Thank you all for listening. It was a pleasure for me to present it today, and thank you for your attention.